Good morning, all my AP Chem students. I hope you guys had a wonderful weekend and are ready to start another full week here in Chem. We are going to be starting a new chapter here on gas laws, and it's a pretty short chapter. It's only about 2 weeks. It'll combine some of the concepts that we learned in regular Chem. And we have two really good labs in this chapter. They're much shorter than the ones that we've done in the last couple of chapters, so hopefully you can look forward to that. And these gas laws, you guys, are very important for our survival, honestly for survival. We have an atmosphere that's going to support life, and we have to have certain pressure differences according to volume and temperature, and those are all the things that we are going to take a look at. So the first thing that we have here is called a manometer. It is a device for measuring the pressure of a gas in a container. So first of all, manometer means one, and you guys can see that this picture here has one open end to our air or to the atmosphere. And inside of here, this is a closed system over here. So we have a closed system, we have a gas inside of there, and gases are colliding with each other, so creating some pressure. And here we have our gas pressure is less than the atmospheric pressure, and over here it is greater. And you can see the difference in the mercury. This is the mercury that's inside the manometer that is moving around based upon the pressure. So we're going to take a look at Dalton's law, which is down here, and being able to measure that height, which is what we'll do in one of our labs to figure out the pressure that is being involved. So the first thing that we have to take a look at is Boyle's law. And you probably remember this from regular Chem. It's a pretty easy law to remember, that it is pressure 1 times volume 1 equals pressure 2 times volume 2, and they are inversely related. So meaning that if the pressure increases, we know that the volume is going to decrease, or vice versa. And if we take a look, this is a pretty traditional graph that you will see on Boyle's law. We have pressure versus volume, and we have this downward curve, and you can take all the values there and see how it supports Boyle's law. And again, if you're going to get a linear relationship, easier to maybe see, then you would do volume over 1 over the pressure. If we get a straight line, then we indeed have Boyle's law. Now this is always going to be true for low pressures. Things that are very high pressures, it's not going to be as constant. There is going to be some deviations, but they are going to be very small. So for all practical purposes, we are going to hold that Boyle's law is always true. So if we look at this diagram, you guys can see that it says as pressure increases, the volume of the sulfur dioxide decreases. What is the volume of the second example? So you guys could go ahead and calculate that out, and but you can see that your value for the volume should decrease based on the pictures that here. And that just makes sense. If I'm increasing the pressure, the volume is going to decrease. And again, that's an inverse relationship with Boyle's law. Okay, then moving right along to Charles' law. Charles' law introduces temperature. And in Charles' law, we had to introduce the Kelvin scale. And the reason for that is because we can't have, we know we can have negative 10 degrees Fahrenheit, negative 20 degrees Celsius, or whatever those values are, but we can't have negative volume. That doesn't really make sense. So Charles' law, he figured out that volume and temperature is a direct relationship, and you can see that volume and temperature, that if they are pressure moles are held constant, we have this relationship. That doesn't look like it's volume divided by the temperature. And you can see that it's V1 times T2 right here, and so that means that they have cross multiplied, because it would be V1 over temperature 1, volume 2 over temperature 2, cross multiply, and you get the formula that we probably used last year. Now if you recall, the Kelvin temperature, you have to take the degrees Celsius and add 273, and that will give you Kelvin, not degrees Kelvin, just plain old Kelvin. And what Sir Charles did is he took all these different gases, as you can see over here, he cooled them down and kept on cooling them down as much as he could, and he found by extrapolating the data that everything came to this certain point. And hopefully you are thinking that that point is absolute zero. And you would be correct. And at absolute zero, all matter ceases to exist. And so Kelvin, or Sir Charles, he figured out that this specific point would be absolute zero, and he used that to develop the Kelvin scale. And so for these gas laws to be true, we have to make sure that we are always converting our degrees Celsius into Kelvin. Now, because of the pressures and all the chemicals that we have, we actually have gotten down to point, let's see, 1, 2, 3, 4, down to that within absolute zero. Very, very close. And with newer technology and newer ways of cooling things down, we might even get closer than that. Okay, so that is Charles' law. I gave you two little examples here to try to calculate, and I'll just write down the answers here for you. One is using Boyle's law, and the other is using Charles' law. I'm quite sure that you can calculate these out. This is in pascals, which is another unit for pressure. We could have millimeters of mercury, we could have torr, we could have pascal. Pounds per square inch. There's all sorts of units for that. If there's anything that they'd want you to convert, you would be able to, you'd be given those conversions. And then the second one, you can see that the answer there is 3.11 liters. Okay, and then the last point that I want to talk about here in this first one is Avogadro's law. Avogadro's law says that these balloons hold 1 liter of gas at 25 degrees Celsius and 1 atmosphere. Now, these are going to be considered standard conditions. 25 degrees Celsius and 1 atmosphere is standard conditions. If you look at the bottom of your periodic chart that we've been using all along, it has those same standard conditions for all of the phases that the elements are on the periodic chart. So what Avogadro is saying is that if I have equal volumes, this should be of gases, because we are talking about gases here, at the same temperature and pressure contain equal number of particles. So the same temperature and pressure, equal number of particles. So he said this famous law that we know, that 1 mole of any gas equals 22.4 liters at STP. And so you can see over here that we have nitrogen, hydrogen, methane, and argon gases. And their balloons are all going to be the same. They all are going to have the same number of particles, 6.02 times 10 to the 23rd, if they all have 22.4 liters and are at STP. Now, this doesn't say anything about the velocities, which we will talk about later in this chapter, but you can imagine that they all have different masses, so the velocities of what's going on in there is going to be slightly different. But for Avogadro's law, that they are going to have equal volume if they're at the same temperature and pressure. And you can see here the formula here, and V is for volume, N is for the number of moles. And so this is just a relationship if I have it at constant temperature and pressure. Okay, so that's the end of our first podcast, and I hope you have a wonderful day, and we'll continue on with gases at a later date.